Okay. So am I audible? Can someone please confirm? Am I audible? Yeah, you can write it in your chat box, yes or no. And also my screen. Okay. Thank you. And my screen is also visible, right? The PPT I am sharing. Okay. Okay. So should we start or can we wait for 1 or 2 minutes to you know join others? Okay, meanwhile, we'll start. Say they will join. So we will continue our discussion. Okay, so good afternoon, everyone. My name is Devasis Ponda. I am a research scholar and one of the Prime Minister Research Fellow at IIT Guwahati. So, for the July-November 2024 uh, semester for the NPTEL, so I have been allocated to the course Reliability-Based Structural Design. And this course is actually instructed by Professor Arunasis Chakraborty. So, what I will do actually every week on Sunday from 3 p.m. to 5 p.m. I will be conducting the interaction sessions. Okay. So the basic question is what we will do during that 2 hour of interaction sessions, right? So firstly, what we will do, we will quickly go through the concepts which will be required to solve the tutorials or assignments related to that particular week. Then we will focus on solving problems. First we will solve on pen and paper, then we will move to MATLAB to solve the problems and do the necessary algorithms and all these things. Okay, so this session will be more interactive. We will be solving problems live. Okay, and similar to your current week assignment, so that you can solve the current week assignment as well as it will be helpful for your final examination. Okay, and now after each session, what I will do, I will provide the link of the recorded session, that video recording session, and the assignments. Actually, we will solve some tutorials related to that assignments and notes. Whatever we will discuss here, I will share it, and also the MATLAB script. So that MATLAB script will contain like problems. Further, we will and move that we need MATLAB uh, like algorithms to solve some problem like second order reliability, first order reliability, and some like simulation based techniques. We need that MATLAB thing. Okay, but make sure like for your assignment and for your final examination purpose, the problems which can be solved using pen and paper, that kind of problems will be given to you. Okay, and that will be very easy. That if you go through that video lectures every week and attend the interaction session, I think you will be able to solve all the assignments as well as the final questions. Okay, so as I said, this session will be more interactive, not like that I am uh, talking to the screen and you are sitting behind there. Okay, so make sure that every interaction session you will be with your pen and paper and calculator if possible. And for the MATLAB, I think the MATLAB version for this course is also added. So you can talk to the NPTEL team, or you can install that student version of MATLAB. That will also be quite enough to solve these problems and algorithms. And later on, you can use other other version of the MATLAB to solve these problems. Okay. So first, tell me, have you gone through the videos of the current week? Yes. Have you gone through? Okay, let me tell you one more thing that reliability-based structural design that when the NPTEL course is that preparing. So I was one of the lead TA of this course. So I quite aware of the questions and that kind of assignments. What would come, and how to solve them. What are the tricks and all these things. Okay, so let's quickly move to like that is the first week module. So if you watch the videos, so you can easily correlate that the first week video is more or less revolving around the theory of probability. Okay, let me first. So it's like theory of probability. So we will quickly touch upon these topics, and then we will move to solve our problems. Like if we go to the syllabus, I hope everyone have gone through that syllabus. So actually, the first 2 weeks lecture are revolve around the theory of probability. Then, when the course progresses, we will see the different kind of reliability methods, mainly first order. Then we will move to second order reliability method. Then we have some like simulation based technique to solve the desired problems, and later on we will see other things like code calibration and some of the advanced problem related to like how to do mathematical FEM modeling, and then we do the reliability analysis. Basically the application part. So almost we will cover these things during that interaction sessions. Okay, so these are the books referred by your course instructor. But for the solving the tutorials, I will be following that Ranganathan book and Hallar and Mahadevan book. You can also follow that Melcher's book for the probability part. Okay, so but what that course actually not dedicated to probability and statistics. It's basically uh, dedicated towards like reliability based structural design. Okay, how we can incorporate that randomness into our design problems and solve them. That's all. Okay, so let's quickly, go through the first week content quickly and try to solve some of the problems. Okay, so till now, do you have any queries? You can ask me. So what I said, it will be a more interactive session. Whatever, question comes to your mind, you can directly ask me. Okay, so shall we proceed? Well, okay. So, you know, the course reliability based structural design, to quantify the uncertainties, we need to use the probability things. Like more specifically, we need to use the random variables to quantify that uncertainty in our like limit state function. If we have a limit state function, how the variables are changing, or what should be the distribution of that variable, and how we can solve it, all these things. So let's quickly go through the concepts of probability, so that that things should get recapitulated. Okay, so probability, that actually start from a random experiment. Okay, random experiment. So whom we call the random experiment? Like if we perform one experiment in an identical condition, then if the outcomes of every time, if the outcomes is not identical, like it may change every time we'll repeat the experiment, the outcome may change. Okay, so we call them random experiment. Like if we toss a coin multiple times, like head may appear or tail may appear. Okay, so we call them random experiment. Now from random experiment we have what we call the sample space. Now whom we call sample space, what is the definition for the sample space? You all know that the set of all possible outcomes of a random experiment. The set of all possible outcomes of a random experiment. Now, okay, we call them sample space. Now, sample space is denoted by like S. If we flip one coin, okay, one say unbiased coin, so what will be the sample space? Either head can appear or tail can appear. So the sample space contain these two events. Events now, if when we know about the sample space, we come to the events. What are the events? Whom we call events? Whom we call events? Like A subset of a sample space we call event. A subset of the sample space, or more specifically, a subset of the sample space associated with a random experiment is called the event. Okay, like here, if I say here we can have two events like head, the probability of occurrence of head and probability of occurrence of tail. Or we can say that if we throw a die, so our sample space will be either it can appear 1, 2, 3, 4, 5 or 6. So that sample space contain this number of events, elementary events, more specifically elementary event. Elementary events, whom we call the elementary events, each of the outcome of the random experiment we call elementary event. Okay. So from here, one more thing uh, is important, like whom we call the impossible event. Impossible event. Like we all know that phi is a set, is a subset of every set. So probability of a null set is always क्या होता है? Always zero, and that is called the impossible event. Okay. Now probability of whole sample space. If we want to calculate the probability of whole sample space, what will be that? That will become 1. So as per the classical definition of probability, what we know that if a event A occur n times out of n trials, or we can say that we have a random experiment, and out of that random experiment, if the na number is favorable to that event, then the probability of occurrence of A will be the na, that means the favorable events divided by n. So here two concepts will come into play. Like we need to understand two things, like whom we call uh, equally likely, three things like equally likely, mutually exclusive and exhaustive event. So equally likely, you all know from the basic theory of probability, like a set of events are said to be equally likely events when the chances of happening of an event is not greater than or less than any of the event. Like if we toss a coin, so there is a possibilities like head will come 1 by 2 and tail will come 1 by 2. So them we call equally likely events. Same as mutually exclusive events, like if one event is occurring, that will suppress the occurrence of another event. Like if we toss a coin, so if head occur, then that will suppress the occurrence of tail. And one more property like exhaustive event. Exhaustive event, we can sum the probability, and if there are E1, E2, E3 events, then the probability of E1 union E2 union E3 dot equals to, or that will give us the sample space. So these are the like classical definition of the probability, and some of the question may ask from here like what will be the probability of a null set? It will be 0. What will be probability of a total sample space? It will be 1. Okay, so that's all kind of like MCQ question may come from this basic concept of classical definition of probability of theory. So we will not spend much time on that. Like it's the fundamental things, you can get it from any books. So we will be focusing on that things that will be required to solve the problems, like more focusing on the random variables. So here after getting the classical definition of probability, there is a problem like how big should be the sample space. So then we uh, have the axiometric definition of probability. Like this is basically depends on three axioms. First axiom says the probability of an event should always be greater than or equals to 0, and the probability of whole sample space is equals to 1. So obvious, because the sample space demonstrate all the possibilities, right? All the events that contained within that sample space. And another thing, like if A and B are mutually exclusive events, mutually exclusive, whom we call mutually exclusive, if two event A and B, okay, listen carefully, if two events A and B are said to be mutually exclusive event, if the occurrence of any of them exclude the occurrence of other. Like if we toss a coin, so our sample space will be head or tail. So if the head occurs, so probability of head is half. So if head occur, then it suppresses the occurrence of tail. So if we have two events which are mutually exclusive, then the probability of A union B, we can write it like probability of A plus probability of B. That means we can add them up. Now, after getting the axiomatic definition, we have the conditional probability. What that conditional probability says, like one event is, if the one event is already occurred, then condition on that we can find out the probability of other event. Like probability of A condition B, we can write it down like probability of A intersection B divided by probability of B, provided like probability of B cannot be 0 because it has already occurred, and we have seen that probability of an event is always greater than or equals to 0. Now, from conditional probability, which leads to an interesting theorem that's called the Bayes theorem. When we progress on this course, we can see that how to use that Bayes theorem to calculate different desired values. Okay, so what Bayes theorem says, like probability of A intersection B, we can write it's like that probability of B given A multiplied by probability of A divided by probability of B. Now, here one more thing is important, like when we call some events as independent, like how we can define the stochastic independence. Stochastic independence, like if we can multiply the probability, here probability of A intersection B, how this is written, probability of A multiplied by probability of B. So if this phenomena occurs, then we call that A and B are independent to each other. So we will more discuss on that stochastic independence, like when we call that two events are independent to each other. Okay, so here if event A and B are said to be stochastically independent if any of the following statement is true, like if either probability of A intersection B, we can write probability of A multiplied by probability of B. So if this condition satisfy, we can say, okay, these two events are independent, or probability of A given B, we can write probability of A. If you recall that conditional probability, what conditional probability says, probability of A given B is equals to probability of A intersection B by probability of B. Now if independent, A and B are independent, so I can write probability of A multiplied by probability of B divided by probability of B, and then probability of B and probability of B are cancel out, so we will have probability of A given B is equals to probability of A. So if this condition satisfy, we can say, okay, these two events are independent, or we can say that probability of A intersection B similarly is equals to probability of A. So if in a question asked that find out these events are events are independent or not, so what you need to do, or you need to find out that if it satisfies these conditions or not. If satisfies, okay, we can say this is these are stochastically independent or independent events. So these are the basics of probability. So we will not spend of much time on probability, rather we will go directly on the random variables, because they are important to quantify the uncertainties in the design problems. So random variables, now focus from this slide, whom we call a random variable. Now through that random variables, the randomness or the uncertainties are included. Okay, so random variable, whom we call a random variable. So basically, it's a single valued function which map the sample space to real number. Now, let me explain this in more clear way. Like if we toss two coins at the same time, so what will be the sample space? Two coin we are tossing at the same time. So either What are the possibilities? Either head will occur, either head tail will occur, or tail head will occur, or tail will occur, right? So our sample space will cover that four outcomes. Now, so this is our sample space. If I draw it down, this is our sample space. Like here, head can occur, head tail can occur, tail head can occur. Now tail can occur. Now, if I want to map that sample space into real number, so this is the set of real number. So what will happen? Like head, if I map it to tail head and head tail, map it with 1, and tail if we map it to 0. So if a random variable x, if we assign a random variable x to map this sample space to real number, then x will take the value of either 0, 1 or 2. Okay. So now we can say that if we need to find out the probability of the corresponding probability of occurrence, so directly we can write p of 0. P of 0, that means it indicates that how many times head will not appear. So obviously we can find it out. So 0, that means we have like uh, occurrence, probability of occurrence is 1 by 4. And similarly, for other things like p of 2, that means the probability of occurrence of double head at a time. So you can find it out. That means simply when we will solve the problem, this will be more clear. For now, to understand what is the random variable, so it's a function which map the sample space into real number. So it can be any number. Okay, it can here I map with 0, 1, 2. I can map with other number also. So basically what it does or it do like mapping things to sample space to real number. Now we have different kind of random variables like discrete and continuous. So here we have seen for the coin tossing example, the variable x can take the value of 0, 1, 2. That means the values are countable, right? So if a random variable, or the number the random variable can take, if these are countable or finitely countable, then we call it is a discrete random variable. For example, like we have seen the previous example of tossing a coin, or consider the number of cars passing through a toll booth in an hour. So it can be either 0, 1, 2, 3, 5, 8, 10, 100. That's all. It cannot be any fractional number, right? So we can count these numbers of the random variable. So if a random variable which takes the values which can be countable, we call them discrete random variable. And discrete random variables are actually quantified by probability mass function and cumulative distribution function. Similarly, we have continuous random variables. Continuous random variables, like the random variables, the values which that random variable will take, that is finite or infinite in number, that is not countable. Or if a random variable takes a values between a line, say 0 to 1, so there may be countless of number, like 0 from 0, 0.001 you can write, or you can write 0.0001, 0.00, like there can be infinite number. Okay, so discrete and continuous, what is the major difference? One, the values we can count or countable, and continuous, it's like the values, if a random variable, the values lies between some interval, or the values is infinite. Okay, we cannot count them. Like consider the height of student in a classroom, so it can be different values, 150.5 centimeter, 150.7 centimeter, so on, so on, so on. Okay, so these are called continuous random variable, and continuous random variables are quantified with based on the probability distribution function and cumulative distribution function. So quickly we'll spend some times on PMF and solve some problem, and PDF and solve few problems. Okay, so PMF, that probability mass function, it's a basic of your statistics. Like if we want to define a probability mass function, then how we can define a probability mass function? So if we have a random variable x with distinct values, so x is a discrete random variable, and we have already learned that discrete random variable possess some or takes some certain values. So now if we want to calculate the probability of a value equal to that specific value, like probability of x equals to x1, what will be that? So PMF will give you that value. So probability mass function Px of x, it is denoted by that, and it will give the probability of that value, particular value that random variable takes, that equals to Pi. And that cumulative distribution function, how we can add this? This is nothing but, you if you sum the all probabilities, then you will get the CDF value. No worries, we will solve some problem that will be clear, very clear. So some properties here, like always the probability mass function is equals to 0. If you recall the axiomatic definition of probability, it says obviously the probability of an event is greater than equals to 0. And if we all add all the probability mass functions, then it will give you 1. That means the area under that curve should be 1. Okay, like here we can say, like same definition what I said, that is here written here, like probability mass function, how can define that? So let's quickly take an example. Like if we have 3 coins and we tossed, then and tossed once, we have tossed once, so what will be the sample space? The sample space will be either that tail head tail combination will occur, head tail head combination will occur, tail head tail, tail tail head, head head tail, and so on. So that means our sample space will contain 2 to the power 3, that means 8 number of events, elementary events more specifically. So now if we assign a random variable x, now that random variable x is associated with that number of how many times that number of head will occur. So head can occur either, look, either 0 time, when it will give that 0 time, when all the possible values will be tail tail tail, right? So it might be 0, it might be 1, 2, or 3, maximum value 3. Now probability of x equals to 0, that means that head will not appear. So one time head will not appear, so what will be the probability? 1 by 8. That means if we write it down in a simplified manner, so p of x equals to 0, that means it denotes your p of p of tail, tail, and tail. Just recall the definition of the random variable. It mapped the that sample space into real number. So we have mapped it. That's why we have written here x equals to 0. So obviously 1 by 8. Now what will be the probability of x equals to 2? That will be nothing but 2. That means how many times that 2 number of head is occurs. So obviously 3 times. So 3 by 8. And probability of getting 3 head at a time. So obviously it will occur one time, so it will be 1. Now what was the definition of probability mass function? Probability mass function says that p x of x is equals to nothing but p of probability of x equals to xi. That means that will be the capital X, okay, equal to xi when your x is equals to xi, and 0 when x is not equals to xi. So if I want to write down the probability mass function of the problem, what I can write it down? So probability mass function px of x can be written as px equals to 0, the value will be 1 by 8 when x equals to 0. When x equals to 1, it will be 3 by 8. When x equals to 2, it will be again 3 by 8. And when x equals to 3, that means the probability of occurrence of 3 heads at a time, so that will be 1 by 8. And 0 when this will be not equals to xi. So by this way we can formulate one probability mass function for discrete random variable. Okay, so rather probability mass function, the probability distribution function, and continuous random variables are most important. Okay, so here a little bit we will talk about the cumulative distribution function. So here, cumulative distribution function, either it can be denoted like fx of x. That means that the probability of the random variable x is less than equals to that particular value. Now here, that capital X, the notation. Now be careful with the notation, that capital X is your random variable, and that small x, the values the random variable can take. This call we state. Okay. So what that cumulative distribution says, that the probability of getting the random variable less than equals to specific values. So if we consider the same problem here, uh, and it says they find out the probability distribution function or cumulative distribution function for this problem, what will you do? So you have already calculated the probabilities for x equals to 0, x equals to 1, x equals to 2, and x equals to 3. Now what? Now you need to identify that probability of x, like probability of x less than equals to 0, less than equals to 0. On the next page this has been written here, the probability of f0 is equals to probability of x less than equals to 0. That means how many values we are, you know before that 0, only one value, that is 1 by 8. Now what is the probability of 1? That means probability of x less than equals to 1. That means we need to add probability of x equals to 0 plus probability of x equals to 1. So if we add them, you will get this. Similarly, probability of 2 less than 2, that means you will add 3 values. Probability of 3, that means probability of x getting less than equals to 3 should be sum of these all values. So by this way we can define the you know uh, cumulative distribution function for a discrete random variable. So these are for discrete random variable, and for continuous random variable it's nothing but you just need to integrate it. Here you do the summation things, and there you do the integration part. Like you cannot not do sum all the infinite values over the interval or period. Okay, so by this way we can uh, find out the PDF and PMFs for the discrete random variables. Okay, now come to the continuous random variable. This is important, more important uh, for this course. Okay, so for a continuous random variable, we have already gone through the definition. Like the values of a continuous random variable can take infinite numbers, or it may be lie within an interval. So for a continuous random variable, so here you can see for a normal distribution, the PDF has been plotted. So this is called the PDF, probability distribution function. So what that probability distribution function says, it says or it tells about the distribution of relative frequency of occurrence of any event. Okay. Now if I want to calculate the probability, like say here there is a point x, so I need to find out the probability of up to this point x. What I need to do, I just need to integrate the area up to this point, and this is actually called your cumulative distribution function, fx of x. What that means? That means that probability of x less than equals to x. That means you have to integrate this probability distribution function from the lower bound to that point. So if the lower bound is minus infinity, so minus infinity to x, if you integrate that probability distribution function, you will get the probability of the value or up to the value x. Clear? So this is called cumulative density or cumulative distribution function. Here the CDF has been plotted. So the extreme value of the CDF is 0 always, and the upper bound is 1. Like simply if you integrate it, like what that fx of x means, like you need to integrate, like if the lower bound is minus infinity, and if you integrate is minus infinity to minus infinity fx of x dx, then obviously you will get 0. And minus infinity to infinity, if we integrate fx of x dx, it will give you 1. That means if you integrate the PDF, or simply the area under the PDF will always equals to 1. So this is important, like MCQ questions may ask from this part. If we integrate the PDF from over all the range, then this value is always 1 for all the random variables. Okay, and like it's always the value will be greater than or equals to 0 as per our axiomatic definition. And one more thing, that CDF of any continuous random variable, it's a monotonically increasing function. Okay, that means the value, when we progress to find out the probabilities, the value should be always greater than or equals to 0. So here two or three things you need to remember, that probability distribution function that tells us about the relative frequency of occurrence or the distribution of relative frequency of occurrence, and cumulative density function or cumulative distribution function, if we want to calculate the probabilities up to some point, then it will, if you integrate that PDF up to that point, you will get the desired values. Now tell me one thing, if we want to calculate the probability of some interval, like here we have A and B 2 points, and we want to calculate the uh, probability between that two, so how we can proceed with that? Like here a point is A and B. Now if I want to calculate the probability of getting X, you know in between A to B, how we can calculate? Just integrate the probability distribution function over this range, you will get the probability. Okay, now tell me one question, probability of a point, what will be the probability of a point? If I say now calculate the probability of a point, just a point, what will be the probability of a point? Say there is a C point, only C. So C to C, if we integrate fx of x dx, what will come? Probability of a point? Tell me, what will be the probability of a point? If we integrate this C to C fx of dx, what will happen? Write it down in the chat box. What will happen? Hmm? Probability of a point, if you want to calculate? Yeah, great. It will be 0. Obviously, that integration will lead to 0. So, 0. Great. So now the thing is, when we will solve the probabilities and solve the reliability based structural design problems, we can avoid doing that integration. Like if we have normal distribution, we have normal tables. Now I will tell how to use that normal table or how to use a calculator to find out these values. Okay, when we later progress to solve the problems, we will see it. Okay, so like quickly solve one problem regarding your PDF. So here, is it visible? So if that PDF is given to you, say x is a continuous random variable and one PDF for x is given, like it will be ax if the range is 0 to 1, it will be a if the range is 1 to 2, it will be that if the range is this, and 0 for anywhere else. Now the question says first determine the constant a. First determine the constant a. Then second question says that find out the probability of x less than equals to your 1.5 value. Now how we can proceed with this problem? First, we know one property of the distribution function. Like if we integrate the distribution function over the whole domain, then it will give you 1. So this is the logic to solve this problem. So here this one, now break into parts. Like here we have 0 to 1 one value, 1 to 2 one value, 2 to 3 another value. So first minus infinity to 0, that 0 value. Now 0 to 1 we have some values ax. Now 1 to 2 we have again some values a, and again 2 to 3 we have these values, and beyond that 0. So minus infinity to 0 and 3 to minus plus infinity we have 0 values, rest we have some value. So if we do the integration, then the a comes as 1 by 2 half value. Okay, so we know, now we know the constant value. So now my probability distribution is completed. Like first one will be x by 2, second one will be half, third one will be like a by 2 plus 3 by 2, something like that. So now we can easily calculate the probability of x less than equals to 1.5. That means if we have like the distribution like this, say for example like this, so and here the 1.5 value. So if we need to calculate the probability up to that point or less than equals to that point, so we need to integrate that PDF up to 1.5, right? So let's say lower bound is minus infinity to 1.5, we need to integrate the probability distribution function. Now we have the probability distribution function with us. So minus infinity to 0, it's 0 because it will not take any values. The range is already provided. Now 0 to 1, we have fx value. 0 to 1, 0 to 1, we have x by 2. So already we have calculated a value. So if you put all these values and solve the integration, you will get half as a probability of x less than equals to 1.5. So what are the logic here? Like two things you need to remember. If we integrate the probability distribution function over the whole domain, it will give you 1. Now, if you need to calculate the probability up to that point, so you need to integrate up to that point. Now, if you want to calculate the probability beyond that point, like x greater than equals to 1.5, you need to calculate the other part of the like PDF. So that will start from like 1.5 to your upper value is infinity. So here not infinity, like up to 3 you just need to go. So your integration will break into two parts, like 1.5 to something value, then 1.5, then that value to 3 value. Okay, so 1.5 to 2 and 2 to 3. And if you do the integration, you will have the probability of x getting greater than equals to 1.5. Clear? Okay, now quickly solve one problem. For this, tell me what will be the value of k quickly. If the probability here only one, range is given. If PDF is given, this is your PDF probability distribution function. Now tell me what will be the value of k here and how you can find it out. Only the find it out k value. Tell me what will be the value of k quickly. Are you solving? So similar way, you just need to, integrate your PDF over whole domain or range f x of x equals to 1. If you do the integration, then you will find out the k value. Let's quickly solve and tell me the value. This is simple integration, right? So here I have added this. So minus infinity to 0, it's nothing. So 1 to 2 we will just get a value. So for 1 to 2, just need to do the integration. So it's a very simple integration. K that will outside the integration, 3x x square minus 2 simple integration is equals to 1. So ultimately we will get k is equals to 6. So by this way, if the PDF is given and uh, you know uh, in any question ask the find out the value of k, find out the probability of getting less than equals to that, so this kind of problems can be handled in that manner. Okay, clear? So do you have any queries up to this point? You can ask me. Okay, so now if we move forward, we will discuss some random variables. So first we will start with discrete random variables, like random variables which are necessary or important to model different kind of problems in reliability, right? So first random variable is the Bernoulli random variable. We all know it has two outcomes, the success and failure. So if we denote the P of success is equals to, like here you can see that probability of x, like here 5 and 10, the x value, that random variable is x. You can say that the when the success is occur, you can assign a value 0 or 1 here. So by this way you can formulate the uh, CDF and probability mass function for this distribution. So it's a basic distribution when like any design problem, either this has two outcomes. Either we can have, uh, the design is passed or fail. So for this kind of problems, we may use that Bernoulli random variable, but it's a basic kind of random variables. Now, come to that binomial random variable, second kind of random variables. Like here, I have added how you can calculate the PDF and mean and variance. We will talk it later in a few minutes. So binomial random variable, actually it has n independent repeated Bernoulli trials, and the PMF of this random variable is denoted by this, where n is the total number of trials, p is the success, and q is the probability of you know getting that failure. So there are two probabilities can occur, either success or failure. Like, uh, for an example, if we want to model it with some problem, so here one example is given. What is the probability of getting 4 head if an unbiased coin is tossed 20 times? 20 times. So probability of single head, getting a single head, is 1 by 2, right? So sample space will be either head or tail. So probability of getting head, one head, is half. Now, what if we repeat that for 20 times? What will be that? Just use that formula. That remember what that probability mass function said, that probability of x is equals to that certain value. So here that n is 20. So probability of x equals to 20 is equals to, just put all these values in this equation. Like here, k is your 4 and n is 20, half up to the power 4, and 1 minus half. 1 minus half, why 1 minus half? That 1 is if half is your probability of getting head, so what will be the probability of getting tail, like failure? 1 minus that probability of getting head, so 1 minus half, so that will lead to this. So by this way you can directly calculate or model one problem, or formulate one problem, and you can solve using that random variable. Now, most important random variable in a discrete series is that Poisson random variable. And this random variable, so this kind of random variables, if you go through the video lectures, sir has well explained these things, so there is no need to explain more. But still, what I need to tell you, like what will be the PDF and PMFs of these random variables, because these are important when we will solve that actual problems, or when we will use that random variables in a functional form and how to solve them. So for Poisson random variable, like Poisson random variable is used to model the isolated phenomena. Isolated phenomena, like there are many problems, many like examples of this. I will just tell you we in a minute. So the PMF of this kind of distribution, we can say that it denoted as lambda to the power k factorial, yeah, exponential of minus lambda. And what is that lambda? This is actually the rate of occurrence. Now, like example of this random variable, we can say number of printing mistake per page by a skilled typist, or number of goals, or number of telephone calls received by a center per interval of time. We can model this kind of phenomena through Poisson random variable. Now here, like one problem is there. This problem is directly taken from the course video. So a business firm received on an average 2.5 telephone calls during this time interval. Find the probability that on a certain day the firm received no call and exactly 4 calls. So here rate of occurrence is given, lambda is given 2.5. Now you know the probability mass function, p x equals to k, that means lambda to the power k divided by k factorial exponential of minus lambda. So if you put all these values 0, put all these values in this form, x is equals to 0, so you will get this. That probability of getting no call is 0.0821. Now exactly 4 calls, just put the value x is equals to 4 here, so you will get this. That means the probability of getting exactly 4 calls is 0.1336. Okay. So now continuous random variable, just we will spend few minutes on continuous random variable, then we will directly move to that problem, so which we are going to solve. So one of the most important continuous random variable is the Gaussian random variable, or we call the normal random variable. So it is denoted by that n, and it has two parameter, mu, that means mean, and sigma, that means standard deviation. So we will explain that mean and standard deviation when we will see that the moments of a random variable, how we can define the moments of a random variable. So for this random variable, what is important, just remember the what is the PDF, probability distribution function, and the probability distribution function for this random variable is denoted as 1 by root twice pi multiplied by sigma x exponential of minus half x minus mu by sigma x. Now x, that is the random variable, x takes the value. Now we can formulate the probably a cumulative density function also. Now how the cumulative density function, we can say minus infinity to x. You just need to multiply or integrate the probability distribution function over the range. Now here one most important thing, like if the mean mu x is equals to 0 and standard deviation sigma x equals to 1, then we call it a standard normal variable. Now the standard normal variable is very helpful to solve the problems. We can directly, get the values, like here phi of x minus mu by sigma. That means if I want to say, for example, for this problem, if I want to calculate the probability up to this point, so what will be that, like if x, this point, say for example this point is 45, so if x of 45, that means probability of x less than equals to 45. That means we can directly write in a form of standard normal distribution, phi of x minus mu x divided by sigma x. Now this phi value, if we know that phi value, that we can easily calculate from the standard normal table. Within a minute I will show how to use that standard normal table to get that phi value. So this is your standard normal distribution. Now we, if x is normal distribution and z is equals to exponential of x, then we call is a log normal distribution. And for log normal distribution, this is your PDF value. Obviously the log normal distributed will take the values greater than 0. That means it cannot go in a negative side. So for standard normal distribution, the CDF, that means up to that point, the probability we can also calculate from the standard normal table, from phi of ln z by z bar and sigma ln z. And this standard normal, that long normal distribution has two parameters, like your z bar, the mean, and sigma ln z. So these two parameters we can calculate using these two formulas. So these two formulae you need to remember, like how to calculate the z bar. It's nothing but if you have the mean of z. Now by this using this formula, you can directly calculate what will be the value of z bar and what will be value of sigma ln z. Okay, so here like there are other kind of random variables are there. So this is the list which I take from the Ranganathan book, so you can go through them, because the parameters of a random variables or the distribution which it takes, that are important, to solve the problems. Now let's quickly spend some times on moments of random variable. Few times back I'm saying that mean, standard deviation, what are they? Okay, they're actually the moments of a random variable. Now why that moments of a random variable important? The moments of a random variable actually tells us about the data, like what if the central tendency of the data, or the data is, how much this is dispersed from the mean, its flatness, its skewness, all these things. So moments can either be defined with respect to origin or with respect to mean. So the moments which are defined with respect to origin, we call them the moment about origin. So first moment about origin is equals to, so if we have to calculate the nth moment about origin, that will nothing but the expectation of uh, that random variable takes the value n times. That means what you need to do, you need to integrate this probability PDF, that means probability distribution functions multiplied by x time to dx. Now if we want to find out the first moment about origin, what will that? So obviously it will e of x, expectation of x is equals to nothing but minus infinity to infinity. That means the whole range that the random variable can take, x multiplied by f x of x and dx for continuous case. Okay. Now second central moment is called mean square. So first central moment is called mean of a random variable. Mean of a random variable. So mean denotes the central tendency of the data or that variable. Now second central moment we call mean square. Now when we study the random vibration theory, that mean square concept also used. Now central moments are defined with respect to mean. Here the moment about the origin is defined with respect to that origin value. If I say that I want to calculate the moment about any point, you can say x minus that e of x minus some any point a. What will be that value? We can easily calculate. Just multiply this value with your probability density function and integrate it over the domain. So central moment. Now central moments are taking with respect to the mean value. So what will be the first central moment? First central moment, if I want to calculate the first central moment, E of x minus mu x, so 1. So first central moment, E, that x value is always mu x minus mu x is equals to 0. That means the first central moment is always 0. Now the second central moment, we call it variance. Second central moment, that means e of x minus mu to the power n. That means minus infinity to infinity. You just need to integrate that thing. Like for second moment, it will be square and it will be square. We call it variance. Variance. And standard deviation is nothing but under root of your variance. So variance is nothing but the second central moment. Like we have third and fourth central moment also. Third central moment we can define like that. Yeah. So just that will become 3 and just multiply that, and that r we call the coefficient of skewness. Third central moment we call skewness. It will tell about you know uh, how your distribution is, either your distribution is right skewed, left skewed, or about the data it will tell us. So for for standard normal distribution, the skewness is always 0. And the fourth moment we call it kurtosis. So for standard normal distribution, kurtosis is 3, and kurtosis tell about the flatness of the distribution, like your distribution and data more or like flat, or it will give some peaks or not. Now this all about the moment. So we have two kind of moments. One, moment about origin. That means e of x to the power n. How we can write it down? Just minus infinity to infinity x to the power n. That nth moment, f x of x dx. Now if you want to calculate the first moment, that is your mean. So here 1 will here, n equals to 1. Second moment about origin is mean square. You can easily calculate. Now why this is important, just I will tell in a minute. Like here some properties of the expectation operator, this is important also. So like, if we have like a random variable multiplied with a scalar, then what will happen? The scalar will come out to the come outside to the expectation operator, and it will give a multiplied by e of x. Now if we have that expectation of a random variable plus some scalar value, so we can write it down u of x plus that scalar form. Now if we have two random variable x and y, so e of x plus y, we can write it down x u of x plus u of y if they are independent. Likewise, if we have two random variables x and y, and the expectation of that x and y will be, we can just multiply it if they are independent. Like these are the properties of your mean. Now similarly, we need to calculate the properties of the variance also. So variance nothing but it's the second central moment. Like E of second central moment, how we can write it down? X minus mu x square, right? So this we call variance of x. Now here, this is an important, you know, equation through which we can easily derive the parameters of a random variable of a distribution. Like variance of x is nothing but the second central moment. Now if we open up that bracket, what will happen? Expectation of x square minus 2x mu x plus mu x square, right? So if we simplify it, what will come? E of x square plus, or we can directly write down minus of that, e of x into mu x. Now here, that mu x is a scalar value, we know the mean value, so it will come out, and e of x will left out, and e of mu square, it's a scalar number, so only mu square will left. So what will happen? So e of x square minus, here we will have 2 mu square plus minus 2 mu square plus mu square, and it will lead you e of x square minus mu square. So we can write it down like that, e of x square. What is that e of x square? It is nothing but mean square value. That means second moment about origin is equals to, what we can write, that mean value square plus variance or sigma square. And this is an important relation. While we will solve the problems, we can see that this relation is important to, find out the parameters of the distribution. Easily we can solve it. If we use that equation, we can easily solve the problems. That means our life will be simpler while solving the problems. Or we can simply write it down like variance of x. Variance of x is equals to nothing but, that is mean square value minus e of x. That means this is the mean value square. Now what will be the properties of variance? Like variance of a scalar number, obviously 0. Variance, what variance tells? It tells about the dispersion of the data. Like if we have a distribution like this, and this is your mean value, so variance will tell you how much the data is dispersed from the mean value. Clear? So variance of a scalar number is 0. If we multiply the variance, if we want to calculate the variance of a random variable which is multiplied with a scalar number, so obviously we will get that a square into variance of x. Now if we have like this format, variance of some scalar and plus multiplied with some scalar value, so this variance of this obviously 0, and here we will get only the b square into variance of x. Okay, so here we have understood the two things about moment. Like the moments can be derived based on the origin and based on your like mean value, with respect to mean value, so them we call the central moment. So second central moment variance, third central moment skewness, fourth central moment kurtosis. These all are important to, quantify or identify, or to describe how the data will behave, or what is the tendency of this data, and how we can model them, and subsequently we can solve them. Okay, so what I said, like for different distribution, you can calculate like Bernoulli random variable. We have seen that the Bernoulli random variable, the probability mass function, we can write it like that. So what will be the mean and standard deviation or variance of the Bernoulli random variable? So you can calculate u of x, you know the PDF value. So you can calculate like this. So for Bernoulli random variable, the mean is 1 minus p, and standard deviation variance is p into 1 minus p. So just go through that derivation portion, you will easily understand, and self-explanatory. Like likewise, binomial distribution, we can find it out the mean value and the variance value. Like just see what the equation or the tricks has been used, that formula, that variance square or variance is equals to mean square minus mean whole square. So by this way we can find out the distributions of, or the parameter of different random variable or distributions. Like for binomial distribution, what will be the expected value or mean value? It's nothing but np. If you solve this or if you go through that derivation, you easily understand these things. Likewise, we can find out the mean and variance of other random variable, what we have just discussed. Like for Poisson random variable, we can also calculate. We have the PDF. So just mean value. So mean value of a, like, if we have a discrete random variable, so what will be the mean value? It will nothing but you just sum the probability mass function over the x equals to, or I equals to 1 to n divided by whole number of sample. By this way you can get the mean value of a discrete random variable. Now, likewise for the exponential distribution, you can find it out. Like for exponential distribution, this is the PDF. If x of x for exponential distribution is lambda e to the power minus lambda x, and it has two parameters, mean and variance, and the mean value of a exponential distribution is nothing but the parameter lambda here, and the variance of the distribution is nothing but 1 by lambda square. Now these two things will be important, what I said, while solving the problems. Okay, so here I have added the mean and standard deviation for other distributions, so just go through it. Now that was the expectation operator. If we have one value, if we have a function, or if we have more nonlinear function, what we can do, we can take the help of Taylor series expansion. And for a Taylor series expansion, what do you know about it? Like if we expand any infinite series with respect to some point, so here this is the way we can expand it. Now if we consider for a random variable, the expansion point is the mean, so we can expand like this. And if we consider the only the first value, so what will happen? So e of z will nothing but your e of that function value gu. That means expectation um, operator, if you apply on both sides, so it will nothing but the mean of that function. We will solve a problem. Now variance, if we want to calculate the second moment, so we need to consider up to the second part. So here that is given here. If we consider up to the second part, and we will solve this, and we put the expectation operator on the both sides, so we'll get that expectation of z minus mu z square. This is nothing but your variance will equals to, you need to differentiate that function with respect to the random variable, the square, into e of x minus mu the square. That means the variance of x. So just we will solve the some problems, so these things will get clear. This is very simple things. Okay, don't need to worry about it. Then we will have joint distribution. Like we, if you have two or more random variables, and we need to calculate the probabilities, so we need to take the help of joint distribution. Like here we have two random variables, x and y. If I need to calculate the probability that x lies between a1 to a2 and y lies between b1 to b2, and if we have, this is our joint PDF. So if we have the joint PDF, then we need to integrate it over a1 to a2 and b1 to b2, the joint distribution dx dy. And for the joint distribution also, if we integrate the whole joint distribution function over the domain, then it will give you the one value. And similarly, if you want to calculate the value of that probability distribution function, if the density function is given, just you just need to differentiate that value with respect to that joint distribution function. So in MATLAB we will see how to plot the joint distribution function, how to get the marginals from them, how to plot the marginals, and more or less when we will see the transformation like Rosenblatt transformation, Nader transformation, these joint distributions will play a vital role. So it's nothing but joint distribution. That means if we have more than one random variable, how we can express their PDFs and CDFs, all these things. So if we have a joint distribution, from that joint distribution we can easily calculate the marginals. So how the marginals can be calculated? Here two random variables are there, x and y. So what will be the marginal distribution of x? It's nothing but you just integrate the joint PDF. This is JPDF. You just need to integrate that joint PDF with respect to dy. Similarly, if we want to calculate that the marginal distribution of y, so it's will nothing but minus infinity to infinity. What will happen if xy dx? Just you need to integrate with respect to x. Okay. Now Here one more important note, like we can obtain the marginals from the joint distributions, but from the marginals the joint distribution cannot be achieved. So find that Rosenblatt transformation come into play, then we will understand why these things are necessary. So for now just leave this thing up to this. Now here the conditional probability are there, like if already one uh, event is occurred, then we can find how we can find out the conditional probabilities and all these things. So we'll solve some problems over it. Now expectation operator in two dimension. We have seen the expectation operator in one dimension. C of x, that give you the mean value. That means you just need to integrate minus infinity to infinity, or the domain of your PDF. So x into f x of x dx. Now if we have two random variables x1 and x2, how we can calculate the expected value? So it's nothing but you just need to calculate that function with respect to joint PDF in both the domain. Okay. Now there we see that this called the variance. Here we call it a covariance factor. So covariance is nothing but E of, that means the second central moment. There we call the variance, here we call it a covariance factor. So x1 minus mu1, that means how much x1 is differed from the mu and how much x2 is differed from its mean. So if you do the sum, it will give you the covariance between x1 and x2. And if x1 x2 are same, the covariance will become the variance. So covariance, how can we calculate? Covariance of x1 x2 is nothing but expectation of x1 minus mu1. That means the random variable x1, how much it differs from its mean, multiplied by the random variable x2 minus mu1. So you just need to integrate it. Here one more important thing is the rho. This called the coefficient of variation. So rho between x1 and x2, that means how much the data or how much these two random variables x1 and x2 are correlated to each other. So rho x1 x2 we can easily calculate like covariance of x1 x2 divided by just sigma x sigma y, the variance one. These are some points regarding your variance algebra. Now we will quickly go to the problem solving part. Okay, that will give us more insights about the problem. So I hope you have understood about you have some understanding about, for now, for the problem solving session you have now some understanding about random variables, discrete and continuous random variables, how to find out the mean and variance of a continuous and discrete random variable, how to find out the PDF, or how to find out the probability up to that point of a random variable. Now let's quickly solve some problems. So till now, do you have any doubt or any questions to ask? So ask me please, or else we will solve like 10 or 20 problems, and that will very helpful to solve your assignment. So if you focus on that part and solve the problems with me, your assignments will be solved, that I can guarantee you. Okay, tell me any doubt or any query. For now, like theory part we will not focus that much, just I recapitulate it, like while I'll solve the problem, you will not feel like it is going over your head. That's why. So do you have any doubt till now, or we will solve the problems? Okay, so let's start with a, it's the tutorial one. So I will give the tutorial along with the solution of the tutorials and corresponding MATLAB script of the tutorials. No problem. So first tutorial says given that there are compressive strength tests. So in a laboratory, the compressive strength test of three sets of 20 batches have performed. Determine the mean strength and standard deviation of the concrete. So here 20 batches. Is it a discrete random variable or continuous random variable? Which we are talking about. Tell me, it's a discrete one or a continuous one? We can count it. 20 batches and some samples are there. It is countable. So it's a discrete random variable. So for a discrete random variable, what is the mean value? So mean for a discrete random variable is nothing but summation of these values divided by total number of samples we have taken. How we can calculate the standard deviation? So first we need to calculate the variance. That means the second central moment. Now second central moment for a uh, discrete random variable case, we can easily find it out like that, like variance of like x is equals to nothing but summation of I equals to 1 to n xi. That means the values the random variable take minus the mean value, the square. Obviously x minus mu. Just recall the variance, the second central formula, and divided by n minus 1. Now why n minus 1? To eliminate the biasness. So when we will study the bias unbiased thing, so this thing will clear that why for a for a discrete random variable, the variance, the formula of variance is n minus 1. So for to solve this problem, what do we need to do? Tell me. So to solve this problem, what we need to do? How we can calculate the mean strength and how we can calculate the standard deviation? Any idea? Any guess? So we have three sets. We have three sets or three batches of the sample. So first we need to find out the average value of these samples. So here I have given a table, so you can see. So we have 20 batches here. We have 20 batches. So batch 20 batches, and we have repeated like three times, three sets we have taken. Like as per our IS provision, we need to take like 6 samples. Here, like we have taken 3 samples. So what we need to do first, we need to average out them. Then we have the sample of 20 values. Now we can calculate the x bar value, like it is nothing but summation of your all xi divided by n. So if you calculate it, the mean value will come as 38.64. Now, how you can calculate the standard deviation? So for standard deviation, you need to calculate like what how much this particular data is dispersed from its mean value. That means xi minus mu value. This is nothing but the mean of a or sample mean or mean of a discrete random variable. So if we do it and sum it, we get this. So standard deviation, how we can calculate the standard deviation here? So it will be nothing but under root of 326.57 divided by 19. That will give us 4.14. Okay. Now we have that two data. Now we can easily calculate the probability of failure of some point, right? Now move to next problem here. Problem number 2. The probability density function of rainfall in a day during the monsoon season is given by the probability distribution function is given, f x of x is given. Okay, now find out the mean and variance of the variable. So if you have the probability distribution function to calculate the mean and variance, what you need to do? For mean, it's the first moment about origin. That means you need to integrate the probability distribution function multiplied by with that distribution over the domain. So here the domain is like greater than equals to 0. That means 0 to infinity x multiplied by, this is your PDF. So 3x. Now if you do the integration, it will give you 1 by 3. Now what will be the variance? Now variance, we know variance is equals to E of x square. That means mean square minus mean whole square. So E of x square, now you need to find it out. So you need to perform one more integration, x square into that PDF multiplied with that PDF into dx. So it will give you 2 by 3. Now you can easily calculate the variance. How we can find out the variance? It's nothing but the mean square minus mean the whole square. So it will give you 1 by 9. That means the mean value will be 1 by 3 and the variance will be 1 by 9. Now this problem we can easily solve if we can recall what are the parameter for a exponential distribution. So this distribution, look at the distribution, f x of x is equals to 3 e to the power minus 3x. Which kind of distribution is that? Remember lambda e to the power minus lambda x, it's nothing but an exponential distribution, and the mean of exponential distribution, if you recall, the mean of exponential distribution is nothing but 1 by lambda, and the variance of the exponential distribution is 1 by lambda square. So here lambda value is 3. So directly you can skip the integration part and you will get the values. Like the mean values will be 1 by 3 and the variance will be 1 by 9. Okay. Now move to our next question. Here we need to go to the standard normal table to use the standard normal table. How to use the standard normal table to solve the problem? So here what the problem says, the compressive strength of M20 concrete tested in the laboratory shows that it follows normal distribution with mean this and standard deviation this. Find out the probability of getting strength less than equals to the design value. So design value, that means your 25 MPa. So we have a normal distribution whose parameters are given like mu and sigma. The mean value and the sigma value is given. Now we need to find out the probability of getting the strength less than the design value. Say for example, this is 25. Now what we need to do, we need to integrate the PDF up to this point. So the PDF of a normal distribution is that, but we can directly skip this in this integration if we can use the standard normal table. So p of x less than equals to 25, that means we need to integrate from minus infinity to 25 f x of x dx, and that will lead to you phi of x minus mu x divided by sigma x. Now for the distribution, phi of the x value, what is the x value here? So 25 minus 31.57 is the mean value and divided by 4.32, and that will give you phi, that standard normal variate of minus 1.5208. Now how we can calculate the probability value from here? So I will quickly go to the standard normal table and I will show you how to use the standard normal table to calculate the probability uh, probability values and to bypass the integration part. So just I will share the that portion. Just one second. Okay. Is the normal table is visible to you? Is it? Just tell me. So I will upload that standard normal table and
Yes.
okay. So the Z value will be that phi of whatever we have calculated from there, phi value. So as per this, like Z value here up to this, like Z value comes as 3.4, we can calculate here. So if you remember, or if we need to calculate a Z value with respect to, say for example, we have, say for example, we have 3.4, and these are like fractional values you need to consider with respect to your Z value. Like we have a we need to calculate the Z value of minus 3.41, so your value will be 0.003. Okay. Now likewise you have other for positive values, here the Z values are given. Like for example, if we in a problem, if we have a Z value 1.7, 1.7 say 8, 1.78, so you need to look at up to this value. This is your 1.7 or 8. This value you need to calculate. So this will directly give you the probability up to that point. So if we go back to our problem, what was the phi value we need to calculate here? The phi value was 1.5208 minus 1.5208. Okay, the problem which we were solving, 1 point, like let me check, yes, 1.5208. So look for 1.52, 1.5, now 2 is here, 1.52, this, right, 1.52. So what will be the value? 0.9353. So what the value we got? 0.06, 1.5, like 1.52. Yeah. So by this way, from the standard normal table, we can easily calculate the values of the probabilities or up to that point. Okay. So let's quickly solve another problem so that this thing will get more clear. Like In next problem, we will get the value of 1.88. So if the value is minus 1.88, tell me what will be the probability. If the z value is minus 1.88, what will be the value of the probability? 1.88. Like I cannot write here, otherwise I can write 1.88 minus 1.88. Tell me what will be the value of that phi value. If I have the z value 1.88, 1.8, look for 1.8. Now why that 1.88 part lies here? So the value will be 0.03. Clear? So this is the actual value, and after 0.8, if you need to add some values, look for upper table and that will give you directly the values. Okay. Now for solving your problems during like for the assignments and also for the exam purpose, the standard normal values will be given to you. The standard normal values are given to you. So you just need to find out which value is suitable for you. Okay. So like for this example, what I was looking at, like the value phi value is 1 minus 1.88. So we have seen that for that 1.88, we will get minus 1.88, we will get 0.031 value. Okay, so let's solve this problem from the starting. What the problem says, the compressive strength of M15 concrete tested in the laboratory shows that it follows the log normal distribution with mean that and standard deviation of this. Find out the probability of getting strength less than equals to 15 MPa. Okay, that means we need to find out the z less than equals to 15. That means we need to 0 to 25, we need to integrate that value, or directly we can get it from the standard normal table. For the log normal distribution, what is that? Z by z bar divided by your sigma ln z. So if you solve the problem, first you what is given, the mean value is given, standard deviation is given. So from there we can find out the coefficient of variation. Why coefficient of variation important? To calculate the sigma ln z, that is the parameter for the log normal distribution. So this is the value of coefficient of variation. Coefficient of variation is nothing but the ratio of your standard deviation by mean. So this comes as 0.239. Now one more important parameter, if you want to skip the calculation part, if your coefficient of variation value is less than 0.25, then del z is you know kind of equal to your sigma ln z. So or else you can calculate the sigma ln z, the parameter of log normal distribution for this. So sigma ln z, how we can calculate? 0. Just del square plus 1 and it will get this, and under root of this it will get 0.325. Now look at these two values, 0.23, 0.23. First two terms you can always can you know consider. Now from here we can calculate the z bar value, that mean of that standard log normal distribution. So it's nothing but mu z exponential of half sigma ln z, so it's come as 23. Now if you put all these values in here, phi of ln 15 by 23 divided by this, so you will get phi of minus 1.88, and phi of minus 1.88, go to the standard normal table and tell me what is the value for this. Can you find it out? Can you find it out from the standard normal table? Yes, we can find it out from the standard normal table. Or we can directly calculate these values using a calculator. Calculator Using a calculator, what we need to do? Just go to the stat mode and you can calculate the p value directly. So do you know that how to calculate that p value using a calculator, or should I explain it? Tell me.
Please explain.
Okay. Like if you have which calculator you have, like 991 ES, FS, whatever you have. Any kind of calculator. If you have any kind of calculator, then like now I have this 991 ES with me. So how we can calculate? Just go to stat mode mode, select mode, go to stat mode, and then here we have a statistical options. Can you see it? Can you see it? The stat options. So go to that stat option and go to the distribution. Go to distribution. Now when we will go to distribution, there is showing the p value. How to calculate the p value? So directly you can get the p value from here. Like for minus 1.88, how much it giving? Minus 1.88, and it is giving us 0.03005, nearly same as your the value which you have got from the standard normal table. So the values here, like for the codes, the calculator are not allowed, so you have to habituated with the normal tables. But still, using a scientific calculator, you go to the stat mode, look for distribution, and look for the p value. You can easily calculate the values from there, or you can easily find it out from the standard normal table. Like, let's solve another example out of it. Here, this is the example I have taken from Ranganathan book. Now what that says, there is a some cube strength and which follows normal distribution with parameter mean is this and standard deviation is this. Now find out the probability that the strength we have getting less than 25. So how we can get it? So probability of the strength less than equals to 25 will nothing but the standard normal variate phi x minus mu x by sigma x, right? So what is the value of x here? 25. What is the value of mean? 30 divided by what is the value for 4.5. Now calculate how much it is coming and tell me the value. Then we will go to the normal table and look for the value and verify the answer. Just solve it and tell me. Phi of how much is coming? Phi of minus 1.11. Minus 1.11. Now go and look for minus 1.11 in your table, or directly if you have calculator, go to stat mode and find out the p value. But for your case, the normal table will be given, so try to habituate with the normal table, or you can verify with your calculator also. And if you know the MATLAB, then your life will more easier, you can directly calculate it. So for minus 1.11, can I share the that standard normal table? Okay, I will share the standard normal table once again and look for the value 1.11. Okay, so is the normal table is visible or it is not visible? Can you please confirm? Like, one second.
It's not visible.
Not visible, right? Okay. Yes, I think now it is visible, right?
Yes.
Yeah. So what was our value? What was the value that we are looking for?
Minus
Minus
minus 1.11.
1.11. So 1.1 here, the 1.1 is here. Now another one, look for that 0.09 here, 1.11, right? This will give you the value of 1.11, yes or no?
Yes.
Now you can easily solve that problem, like the value will from here, like one more thing, if we have the minus value, we can directly 1 minus this thing and get the positive value and do the same calculation for this also. So similarly, this normal table is giving you all the z values and corresponding probabilities. Now to calculate the inverse probability, we also can use this table for to calculate the inverse probability. Like we have to calculate phi inverse of something. So you need to look for these values and look at this, that inverse value corresponding to which z value it you know correlates. Okay, so now let's go to our problem and see what is giving. So here, like if I want to calculate through the calculator, what is giving me, yeah, it will giving you the same value 0.1335, like whatever we have here considered for this 0.1.1, 1 minus 1.11 minus 1.11, yes, 0.1335, and your calculator also give the same value 0.1335. So you can check and verify that you are getting the same values or not. Okay, so now let's go to our problem. Okay, so now is the screen is visible? So 5 of minus 1.11, how much we have got from that standard normal table? 0.1335. So that will be the answer. Now, one more question is there. Probability of less than 40 and greater than equals to 30. Now solve the problem and tell me. Less than 40 but greater than equals to 30. That means that your probability should be lie between 30 Newton per mm square to 40 Newton per mm square. So what do you need to do? You just need to subtract the value. That means f of x 40 minus f of x 30. That means here I have already written it here. That means fx of 40 means fx of 40. That means nothing but phi of 40 minus the mean value 30 divided by your 4.5 minus phi of 30 minus 30 divided by 4.5. Now, if you solve it, you will get that phi of some value. You can take it from the standard normal table and this phi value, and you will get this. Like here, we can verify the results. We get 1.335, and they are getting 1.3333. So here, like actually, they have what if they have done? They have considered like up to 3 or 4 terms. So 1.33 up to 2 terms, it's enough. Okay. Now get it how to calculate the probabilities using the standard normal table. Yes or no? Do you have any queries? Ask me. If not, then we will move further. You want to solve some odd more problems here? So here, similar kind of example, like if we have a PDF, and if the PDF is given to you, you can find out the constant value. We already solved this kind of problem, and if we can solve the constant value simultaneously, we can find out any probabilities lies within that PDF. Okay, so this problem we will get it from Ranganathan book. It's an easy and simple problem. Now here again another problem. It's directly taken from your course material. So here what that problem says, like you have a lateral frame, and the more importantly we know the PDF. Okay, the PDF is given to us. What says we need to find out the mean and variance. Mean and variance. So how I can find out the mean and variance? Mean is nothing but the first moment about the origin. That means you need to integrate your uh, distribution function with respect to the values for this random variable, say s of s ds. So if you integrate this, you will get this variance. It's the second central moment. That means s minus mu s the square. While you have got that mu s value, just put it here and do the integration. You will get the variance. Now, if someone asks after getting the mean and variance value, what should be the probability of getting that strength less than equals to say 1.5? What do you need to do? You just need to integrate it up to that value. So here the lower bound is 1, right? For the PDF, the lower bound is 1. You don't need to go up to that minus infinity part. So only start with 1. So 1 to 1.5 ds. And if you solve the integration, you will get that value 0.654, right? Okay. So now next problem here. Okay. Now this problem, I suppose you should you know, try to solve it. But that problem says the yield strength of steel X follows log normal distribution with mean is given and standard deviation is given. Okay. Now, what is the probability of getting a yield strength value less than 1450 Newton per mm square? Use standard normal table. Also plot the plot thing. I will show you how to plot it, and I will upload these things. So it's a log normal distribution. Mu and sigma is given. So first we need to find out the coefficient of variation. Coefficient of variation is nothing but your sigma by mean. So sigma value and mean value is given. So that comes as this. Now we need to find out the sigma ln z for the log normal distribution. So it comes as 0.035. Just remember, like if it less than 0.025, then your del x and sigma ln x nearly similar values. Look at this, the values quite similar, right? Same, exactly same. For this case, exactly same. But for the previous case, we have seen that there is little difference in after 3 digits. Okay, so while we have these two values, sigma ln z, we can calculate the x bar value. Now when we can calculate the x bar value, so we have, like for the log normal distribution, we have the mean value. This, that means the x bar or z bar, whatever you want to denote it, and the uh, standard deviation value for it. So what will be the value that we will get, that probability of x less than equals to your 1486? That means nothing but phi of ln z by z bar divided by sigma ln z. Just you need to remember this formula for log normal distribution, how we can use the standard normal table for the log normal distribution. So if you solve this, we will get phi of minus 7.6. Now go and see the standard normal table. What will be the value for minus 0.76? It will give you 0.2237. Just cross verify and check. Okay. Now, like here, what we have a question like the total load on a column, including the dead load, live load, and wheel load. Okay, and the load combination, the function for the load combination, it's a linear combination. What is given, like dead load plus live load and wheel load, and the dead load, live load, and wheel load, they all follows the normal distribution. Dead load follows normal distribution with mean and standard deviation. This live load follows normal distribution with mean and standard deviation, and wheel load is also followed normal distribution with mean and variance. What this question asks from you is calculate the probability of the strength of the column is greater than 14.75. Okay, so MATLAB part, just leave it now. Just try to solve it using pen and paper. So we have three random variables, like for dead load, live load, and wheel load. So mean, what will be the mean value? For a linear function, we can just add them up. So mean of s will equals to just mean of the dead load, mean of the live load, mean of the wind load. So if you do the mathematics, it will add them, it will come as 14. What will be the variance? So it's a linear function. The variance will be nothing but the variance of dead load, variance of live load, and variance of your wind load. So if we know the variance like this, we can find out the standard deviation. Standard deviation is nothing but under root of variance. So this is your variance. Now we have mean and sorry, this is your standard deviation. So if we have mean and standard deviation, so what will be the probability of is getting more than 14.75? That means you need to calculate the area on that side, right, greater than of that value. That means it is nothing but 1 minus phi of this part, because the if we integrate the whole PDF, or the area under the whole PDF is always 1. So phi of your x minus mu x by sigma x. Now you have, if you have the mu x and sigma x values, just put it here, and phi of, look at the normal table, phi of 7853. What will be the value of 7853? It will get, and that 7837 or 7838. Can you check, what will be the value of phi of 7853? 0.7853. So we can go up to only 0.78, so we'll get something nearest value of that. Okay, so you can check, cross check these things with the normal table and for the calculator also. it's same problem, like greater than equals to that. That means here you will have the again 1 minus phi of your x minus mu x by sigma x. Now calculate the values. Here the mu and sigma is given. Now if you calculate it and from the standard normal table you will get 0.06 values for this problem. So here another problem. Here one function is given where we have like 1, 2, 3 and 4 random variables. Now here that says that the applied stress on a beam is expressed by this expression where m, the moment, it's like the beam is subjected to axial and bending both at a time. So m by z plus p by a, p by a for axial load and m by z for bending. Now m, that moment will follow the normal distribution with mean 5 and standard deviation this, and p will follow this. Like cross sectional area a is a deterministic value, it's not random. Z also follows normal distribution. Now, the question asks the find out the modulus of the beam and determine mean and standard deviation of the applied stress if the rho is also given. Now, rho things we need to do like when we see that for a nonlinear function, when we expand the Taylor series, we'll see that e of z, e of that function will nothing but that expectation of this function itself. That means if we have the function s is equals to this, so expectation of s will nothing but just take the expectation of these values. That means the moment of these values. So we have the the mean of this moment like 5, say 5 here, the kilonewton meter, so make it newton, so 10 to the power 6 newton mm divided by mu z, z for z also that is given 16 into 10 to the power 5. The unit is here mm, so be careful with the unit. Okay, so if you add them up you will get that 3.81 newton per mm square will be your mean value. Now how you can calculate the variance? So variance is nothing but you need to first differentiate your function with respect to different values. So here we have how many random variables? We have m, we have z and we have p. So first we need to differentiate that with respect to m, then with respect to z, then with respect to p. So here if you do it, the derivation and expand this series, so covariance of x1 and x2 covariance are given, covariance of m and p is given, so here covariance of n and p is given, are used. So by this way you can find out the variance, and variance once we get the variance we can easily get the standard deviation. It's nothing but that 0.525, so this will be your standard deviation. Now when we will get the mean and standard deviation for this distribution, now if say if further in this question ask if find out the some probabilities up to that point, what you need to do, just use the standard normal table, phi of that, if less than, so you need to find out the p value, if greater than 1 minus that p value. That means the you need to first identify the area which you need to calculate, either it's from the left hand side or the right hand side. So by this way you can handle these problems. Similarly we have problems like here there is a point load in the middle, and the deflection here is given as mu delta. So it's a simply supported beam, point load in the middle, so it's nothing but pl cube by 48 ei. So here this p and e, these are like random variables, the values are already given here, I is given, but l and I, these are deterministic value. E is here following normal distribution with mean that and standard deviation that. P also a normal distribution, mean and standard deviation. Now if you need to calculate the mean, you just put all these values in this equation, like mean of that del will equals to mean of all your random variable within that function. So you can get the mean value as 25. Now if you want to calculate the variance, what you need to do, first here look at this, how many random variables are there, p and e. So first you need to differentiate your function with respect to p. So delta by del p will give you that, del delta by del e will give you that, and variance, what will that variance says, variance of z is nothing but you square of that value multiplied by this and plus similarly for the second part you will get this, and by this way this simple formula, this formula you just need to remember. Okay, so here for this, here covariance were given. Now if the variance are there, directly variance things are correlated here. Now this way you can find out the mean and standard deviation of a function or of a given random variable. Like this problem, this is taken from the course material. Like moment of resistance is a function where there are b, d are the random variables. So if you can find out the moment, it's nothing but the moment, mean of this moment. Mean of this moment will be nothing but moment of resistance is nothing but mean of this. Now variance, you need to find it out, the derivations with respect to the random variables and multiply with uh, the variance of this particular random variable. So it will come as this. Now probability of failure you can easily calculate. Now I think you can able to calculate the probability using the standard normal table. Like if the capacity is 650, that means this is my x value, x minus mu x by sigma x. That means ultimately first you need to identify the parameters, like what will be the mean value, what will be the standard deviation value. First you need to find out the function which are given to you is a linear function or a non-linear function, and accordingly you need to do the derivation and multiply with your variance or covariance. If you multiply with that covariance, that correlation coefficient will come into play, and if they are not correlated, then only the variance part will come into picture. Now it's similar kind of problem, it's also taken from your that course material. So here that the deflection of the mean point is considered. So here two kind of loads are there. One uniformly distributed load and one point load is there, right? So what will be the mean deflection at the midpoint? It's nothing but PL cube by 48 EI, and for the distributed load 5WL cube by 38 EI. What will be the mean? It's nothing but mean of these plus mean of these. So here look for L is a deterministic value. E follows normal distribution, that means I random variable. Also W, that means the distributed load follows the normal distribution. Also P follows the normal distribution. So obviously we need to, to find out the variance, we need to first differentiate with respect to P. So del delta by del P, it will come as this. Del delta by del W, if we differentiate it, that will come with this, and you can cross check these things also. Now we can find out the sigma value, sigma of del, that means the variance of del. It will nothing but the differentiate with respect to the variable square multiplied by sigma p, that means the variance of that random variable plus other random variable. So that comes as this. Now the question says the design it against the serviceability limit state. Okay, so what we have the mean value this, and we have the variance this. Now how can we design? That means we ultimately need to find out the I value. How we can find out the I value? It's nothing but what we need, what we know, that phi of 16 minus mu delta. 6, why 16? The allowable deflection is 16 mm. That L by 2 something tha 250. L by 250. So L is 4 meter, and if you do that math, so it will come as 16 mm. Okay. So 16 minus del, that means that will cover the 1 minus probability of failure. So 1 minus probability of failure is given as 10 to the power minus 3. So 1 minus 10 to the power minus 3 will give you 0.999. So ultimately what we have, phi of 16 minus mu delta by sigma delta is equals to 0.999. Now how we can further move? We need to calculate the phi inverse value, right? 16 minus mu delta by sigma delta is equals to phi inverse 0.999. Now how we can calculate that phi inverse 0.998 value from the standard normal table? Do you have any idea, or will I show you? Phi inverse, how we can calculate phi inverse? So in MATLAB, just ICDF, you just write down the command, it will give you the inverse CDF. But from the standard normal table, how we can calculate it? I will show you in a minute. So just remember the value 0.999. we need to calculate the inverse. That means we need to find out the corresponding z values. So if I share the screen again, 1 second. Yes, the screen is visible, right? So what was our value? 0.9999, right? Triple nine. So look for 0.9999. Here we have 0.999. Yes or no? Right? 999. So, or do we have any other value? No. So, or here we also have 0. Yes, here also we have 0.9995. So we can either fix it like 3.09 or 3.1, whatever value you want to take. So 3.09 the nearest value to it. So our answer will be phi inverse of 9, phi inverse of 0.999, that leads to the z value is equals to 3.09. So let's go to there and like solve the problem. The look, that comes as 3.09. Now when we have this value, we can easily solve I is equals to this. Now when we have I, now we can easily design the beam. Like if we consider is a rectangular section, so BD cube by 12 is equals to that. Now we consider some ratio between B and D, and we can fix the B and D accordingly. Okay, now similar kind of problems I have added few. So like here you need to design against the moment capacity at the main point. You can solve it easily, go through that this material. I will upload this material, you can go through it. Okay, some other problems I have also added to here, so you can also go through them and can easily solve them. So actually we have limited time, so if you have any questions you can please ask me. Otherwise, we will quickly go to the MATLAB part. So today I think time will not permit to show the MATLAB scripts, but I will upload the MATLAB script along with that lecture material and videos. So Ritesh and Bob, can you unmute yourself?
Yeah.
Yeah, Bob. So do you have any questions regarding that particular tutorials or any other things which you need to solve your questions?
No, the tutorials was fine. All I need is to take time and go through it and understand it better. So the materials you are talking about, if you can make them available, maybe as the video, and also if there's a PDF version, so that we can always go through and then try to understand it. Thank you very much.
Yeah, I will share the video as well as the lecture material and the MATLAB coding, MATLAB script actually for the problems which like you need to solve using MATLAB. So I will share, I will upload this and you will get the link soon. Okay. Yeah, you need to choose the things like in that 2 hours we almost cover like statistics, how to solve the p value, n value, and it's quite fast. And you need to like
Exactly.
yeah, it's a course advanced level of course. So these are the basic prerequisites like probability, statistics, distributions. Further when we'll move to reliability level 1, level 2 reliability, like it will be more like algorithm based problems. We cannot solve the first order reliability problem after second or two iteration by bare hands, right? So yeah, it will take time, but it's a very easy task to solve your assignments as well as your final semester questions. And Ritesh,
Do you have
yeah,
do you have some previous videos on YouTube?
previous year videos.
Yes.
Actually, this course is a repeat course. So previous year, actually we have launched this course on previous year. I was the mentee of this course. So I have the materials with me, but I think the lecture videos are uploaded in your course portal itself. First week and second week lecture videos are there, right?
Yes, yes, they're there.
Yeah.
Yes.
Along with that, I will upload that interaction session videos, and if you go through them, I think it will help you to solve the problems, particularly the problems you need to solve for your assignments, right?
All
Okay.
right, last one. I joined a bit late, so I didn't get your details. In case one wants to contact you, what details should we use?
What details? Details of regarding what? My details.
No, no, just other email or I mean email in particular.
Oh yeah, yeah. I will say it. No problem. You can mail me. No problem. I am very much active there. One second. Actually, this course is like research level course. So probability and statistics, these are the basic. When we'll do the coding and algorithms, that will actually, give us that feelings of doing that course reliability based structural design. Like when we solve that simulation based techniques and all these things, then is my screen is visible to you? Like
Yes, it is. Yes.
yeah. So this is my mail ID. Mail ID. You can mail it to this mail ID. So I am very much active on there. So no problem. Any kind of queries, I will help to solve. Okay.
All right. Thank you.
Yeah. Thank you. Ritesh, you are
No,
ready
sir, I
now?
have no.
Yeah.
I am from Raipur, sir.
Do you have any doubt?
No, sir, not now.
Okay. So have you solved the assignment one?
No, not yet. I will solve in a later day.
Okay, so just go through that interactive session video. I think you will find similar kind of questions here, and you can easily solve it. But one thing, uh, you should attend each and every interaction session. So today is like the basic thing, and I move bit faster. But from now and onwards, we will solve the problem simultaneously. Okay, you
Sure,
should
sir.
come up with your calculator and pen and paper. I will upload that necessary documents like books, two books and normal tables, whatever is needed. You just be with that so that your assignments will simultaneously get solved and the things get more clear. Okay.
Yes, sir.
Okay. So Ritesh, what are you from?
From Raipur, sir. Raipur, Chhattisgarh.
Raipur. You are doing MTech or PhD?
BTech, sir.
Huh?
BTech, third year.
Okay. So if you have no other queries, then we can end the session here, right?
Yes.
Okay.
All right. Thank you very much.
Thank you, and we will meet you again on next Sunday from 2
Yes.
p.m.